Hello, my name is João Dick. I'm an undergraduate research assistant and student at the Federal University of Rio Grande do Sul, and in this video I'm going to present an overview of the paper Quality and Complexity Assessment of Learning-Based Image Compression Solutions. The demand for multimedia services has experienced a significant growth in the latest years, making image and video content account for most of the web's data traffic. Therefore, image compression solutions play an important role in supporting efficient multimedia transmission and storage. In this context, several models with different characteristics have been developed in the past, combining transforms, operations, and hand-tuned parameters. In the past few years, a new paradigm has been proposed: learning-based image compression. Opposed to the pre-existing models referred here as classical, learning-based models apply convolutional neural networks to image compression. The majority of parameters is no longer hand-tuned, but learned in a training process that aims to minimize the distortion at a given compression rate. This new approach is possible due to abundant training data, hardware computational advances, and new CNN architectures. Neural image compression has different architectural approaches. Nevertheless, most learning-based models can be abstracted to a standard autoencoder scheme, with the encoder E, the probability model P, and the decoder D representing neural networks. The architecture just describes implies a visual quality loss between the original and the reconstructed images, with different visual quality metrics being used to quantify the loss magnitude. Along, a complexity penalty inherited from the model's architecture is expressed in compression and reconstruction execution times. When designing an image compression model, a trade-off can be established between the overall visual quality and overall computational cost. We therefore propose to analyze multiple classical and learning-based models, addressing the trade-off between visual quality and model complexity. Also, easy-access low-cost hardware is utilized to run the experiments on both CPU and GPU. We apply the following methodology. The codec dataset, composed of 24,768 by 512 8-bit RGB images, is utilized to average all metrics between different images. The classical models addressed are JPEG 2000 and BPG, an image codec based on the AGVC intro standard. In the learning-based side, 8 pre-trained models available at the TensorFlow compression framework are considered. When addressing complexity, model size, compression, and reconstruction times for both GPU and CPU are measured. For visual quality, PSNR and MS-SSIM are computed in the luminance channel and LPIPs across RGB. So, let's pass into the results. For an easier visual quality comparison, the mean PSNR and MS-SSIM performances across a common bitrate interval are displayed here. This plot shows that BPG presents the best overall PSNR performance and the second best overall MS-SSIM performance, significantly outperforming JPEG 2000. In the learning-based side, the variational autoencoder VA-min has the best overall MS-SSIM performance and second best PSNR values. The PLR and BGDN neural architectures present the lowest PSNR values but overall competitive performance in MS-SSIM. The complexity inherited from the model's architectures can be evaluated when comparing execution times. This plot presents a relative execution time axis and demonstrates that learning-based advances in visual quality performance came with a significant complexity increase. On the other hand, the big performance evolution from JPEG 2000 to BPG has little impact on execution times. After analyzing the experimental results, we can see that learning-based models obtain significant rate distortion progress in the past few years. On the downside, a considerable computational cost was inherited in this process. That's particularly harmful for image decoding that's usually performed in devices with computational constraints. In our future work, we plan to study the impact of model-efficient optimization and asymmetric architectures in the rate distortion computation trade-off. Detailed results and further discussions are available at our paper manuscript. Thanks for watching.